I got a request to talk about an amino acid at different pHs. Before we do that, I wanted to review how to look at a particular functional group at different pHs given its pKa. So let's say we've got a pKa of 2.2 for a carboxyl group. So you could either be COOH or COO minus. When pH equals pKa, in this case 2.2, you're going to have 50% of each of these forms. If you go one below pKa, then the acidic version of the group, or the protonated version, will not have donated that much of its hydrogen. So at any given time, 91% of these groups will be protonated and only 9% will have been deprotonated. If you go in the other direction and go 1 pH unit above, the opposite is true. The group has been deprotonated to a large extent, and the protonated version is in the minority. That's 1 pH unit away. When you go 2 pH units away, the change is pretty much all one version or the other. You could do Henderson-Hasselbalch to figure out any of these points, but you basically can be confident knowing that 2 pH units away, you're basically all or nothing, or all one form or all the other form. And any more than 2 pH units away, it's going to be even more dramatic, one direction versus the other. So thinking about an amino acid like glutamate, you could draw the structure out, and I'm not specifying the pH just yet. So I would draw or write the pKa's next to each group. So the pKa of the amino group for glutamate would be 9.7, and that's a value that I would provide to you on an exam. You don't have to memorize pKa's at all. The carboxyl group off of the alpha carbon, pKa is 2.2, and the carboxyl group off of the R group is 3.9. So if we were to consider, actually, it is 4.2. So if we were to consider, what does this molecule look like at pH 6.3? You just consider each of these groups separately. So looking at this carboxyl group first, because its pKa is 2.2, by the time that this molecule reaches 6.3, this group would be completely deprotonated. So there'd be a -1 charge if you were calculating the overall charge of this molecule. Going to the next group, the pKa is 4.2, and that's 2 pH units below the pH. So by the time that this molecule gets to a pH 6.3, it will have gotten completely deprotonated as well. Leaving a negative charge. Now looking at the third group is the amino group, and that's got a pKa of 9.7. So at 6.3, this group hasn't started deprotonating yet. There's over 2 pH units difference between these two, and the pKa is higher than the pH. So we'd know that this is totally protonated, and there'd be a +1 charge. So to calculate the overall charge, you just add up your charges, and in this case, the overall charge would be -1. Now for another example, let's say the pH of the solution is 12. What would the overall charge be? So you'd revisit every group again. With a pKa of 2.2, this group would definitely be deprotonated by the time it reached pH 12. The same goes for this other group that has a pKa of 4.2. Now the amino group has a pKa of 9.7, which is below the pH that we're asking about. So by the time this group does get to pH 12, it will have become completely deprotonated. And it will have gone from a NH3 to NH2. So the overall charge of the molecule now would be -1 plus -1 plus 0, which is -2. One thing to keep in mind is that the pHs that I've given in these two examples are far enough away from these pKa's that you could just estimate all deprotonated or totally protonated. If you're closer to the pKa of any of these groups, then for that group you'd have to do Henderson-Hasselbalch. So for example, if I were to say calculate the overall charge of this molecule at pH 2.1, you'd have to do Henderson-Hasselbalch for this group to figure out the partial charge, because it wouldn't be a whole number. And there are examples of this in lecture as well as the practice exam that contains solutions.